Let's talk about propellant depots in space, or refueling without them, as SpaceX is preparing to do. In the past, for deep space missions, upper stages or payload spacecraft typically had propellants like hydrazine that were liquid on Earth or in space and didn't require extremely low temperatures for storage. Today, however, most new rockets use cryogenic propellants for all their stages. Cryogenic means cold, typically about below minus 240 degrees Fahrenheit. An example would be hydrogen and oxygen. Those are used on SLS and on many earlier rockets. But in a newer generation like Starship, they're using methane and oxygen. And you have hybrids. Falcon 9 uses liquid oxygen as an oxidizer, but the fuel is a refined version of kerosene. This drawing was an artist's concept for a NASA program back in 1971. So the idea of storing propellants in space is not new. Why would you do that, though? Mainly because it takes so much propellant just to get into low Earth orbit. You'd like to refill the tanks. Essentially, you want a gas station in space, so you can go wherever after that, Moon, Mars, and so on. But the propellants require cold temperatures for storage as liquids, which you need because liquids are much more dense than gases. NASA has restarted activity on propellant depots. Marshall Space Flight Center, in particular, recently posted progress on storing very cold propellants, that is, below minus 240 degrees Fahrenheit, which is needed for fuels of choice today oxygen, hydrogen, and methane. The biggest issue is boiloff. Any heat, whether from solar radiation, reflected sunlight, or equipment, warms the spacecraft, and some of that heat finds its way to the propellant tanks. That causes liquid propellant to boil into gas and be lost. The longer you're out there, the more you're going to lose. So, the question is, can you achieve zero boil off? That's useful for propellant depots and for spacecraft as well. NASA is in the middle of this 90-day vacuum test with that zero boil off goal. They're already showing you can have zero boil off with liquid hydrogen. That's the hardest to store because it's the coldest. They use active cooling, refrigeration, with two nested layers of insulation and cooling coils with helium. That test is still ongoing. The picture on the right is their test apparatus. When it was all packaged up, this is what it looked like as they dropped it into the giant vacuum test chamber in Huntsville. At NASA, propellant depot was almost a forbidden phrase for a decade. It may have only been a slight exaggeration that even mentioning the word depot could be a firing offense. There are enough stories of people being forced to resign after publishing support for depots that it seems to be true. The reason was that the Senate demanded that the new heavy lift program, the SLS rocket, reuse shuttle parts and, most importantly, the contractors. But with depots, you don't need such big heavy rockets because you have the refueling. So that was really viewed as competition. So depots were politically discouraged. Along the way, NASA kind of indirectly snuck in a dependence on propellant depots, essentially evading the design by the Senate. They did this when they picked SpaceX Starship for the Artemis Human Landing System, acronym HLS, for landing on the moon. That requires loading propellants in Earth orbit to get there. They did require a demo flight to demonstrate the propellant transfer in orbit as well as a demo landing. So SpaceX has the responsibility, but NASA in reality has been involved in this. For instance, they helped develop detailed fluid dynamic calculations of the propellant transfers. Propellant boil-off is an issue if you're going to run a gas station in space, but it's also an issue for long trips in a spacecraft. Going to Mars and back highlights both of these cases, worse really than the current case of just going to the moon. First, the trip times are much longer, 7 to 9 months each way, and because of limited launch windows, you may have to wait a while to return. The total trip could be as long as a few years. You can't have much of your propellant boiling off your spaceship, or you won't even be able to decelerate to finish the trip. And second, once you're on Mars, you need propellants to get back. So, if you land with all your return propellants, they have to be stored for possibly a long time. Or, if you make the propellants on Mars, which is the long range plan, you need to store the production during the stay. Finally, it takes somewhat more propellant for the round trip compared to the moon. This makes orbiting propellant depots even more necessary than for the moon. As an aside, it doesn't take as much more propellant to go to and from Mars versus the Moon as you might think. The time is much longer because of the distance, but you're coasting most of that time without propulsion. You're really just making a few orbit-changing burns. So time is the issue more than the burns themselves. You need more propellants for Mars because you need to escape Earth's orbit, reaching Earth's escape velocity. You don't actually achieve that on the Moon because the Moon itself is orbiting Earth. Also, another factor is the Mars gravity. It's double the Moon's, so you need more propellant to lift off of Mars for the return trip. However, you can do better than the Moon on your descent to Mars because you can do some aerobraking on Mars. That is, you get some slowdown from air friction, dissipating energy, heating a heat shield, and then maybe parachutes. You can't do that on the Moon, where propulsive landing is needed. There's just no atmosphere there. So this means fighting gravity solely with propulsion. People argue about the cost of going to the Moon or Mars first, but besides the factors already mentioned, the long trip to Mars does mean a need for more shielding, that's for radiation or micrometeorites, and you need more redundant parts because replacement shipments just can't happen quickly. I mean, it take a couple of years to get there. And you also need a lot more supplies, such as food. All that cuts into the payloads. And that really factors into the cost of actually going. Getting back to propellant depots, here's one we think. This is called Blue Ring from Blue Origin. Few had heard of this until the first launch of the New Glenn rocket by Blue Origin in January this year. In that New Glenn announcement, they mentioned that, oh, by the way, there was a blue ring in the payload. It's hard to guess the scale of this from the picture, but presumably it fits in the New Glenn rocket payload fairing, so its diameter is probably close to 23 feet. Presumably, propellant tanks and spacecraft would then be attached to the ends or sides. Blue Origin is generally very secretive, but they advertise Blue Ring on their website as a multi-purpose platform. They say it can be a propellant depot, a space tug, a satellite launch platform, or a platform for payload hosting, meaning the payload stays with the Blue Ring rather than launching off in a satellite. Is it real? Probably, but we don't know about its development schedule. On that New Glenn inaugural flight, they really only took a partial prototype of Blue Ring. It didn't separate from the rocket. They said they were just testing the avionics, the electronics. You don't necessarily need a dedicated propellant depot for a fill-up in space. The SpaceX plan is to send up a Starship, then send up a series of tanker Starships that transfer propellants directly to it. You accomplish the same thing, refilling in orbit, but there's no independent propellant depot. This probably makes the most sense initially when there isn't enough demand to justify the expense of a dedicated depot that wouldn't get used very often. The propellant transfer test between two Starships is scheduled for next year, although a lot of people are worried that date will slip. That test is on or close to the critical path in the Artemis plans, meaning any delay there could delay the Artemis 3 mission, which lands people on the Moon using the Starship-based Human Landing System, or HLS as it's abbreviated. So, let's dig a little deeper into the challenges with propellant transfer in space. First, just how cold are we talking about? Here's some examples looking at boiling points. At atmospheric pressure, hydrogen boils at minus 423 Fahrenheit, the coldest by far. For comparison, absolute zero in Fahrenheit is minus 460, so you're within 37 degrees of absolute zero. Now, oxygen boils at a much warmer minus 297 Fahrenheit, and methane boils at a toasty minus 259 Fahrenheit. So, for comparison, the substance with the lowest known boiling point is helium. Its boiling point is minus 452, which is just 8 degrees Fahrenheit above absolute zero. But the propellant tanks will not operate at atmospheric pressure, and boiling points do depend on pressure. You can see this in the example phase diagram for oxygen, shown in this diagram on the left. It tells you the phase, like solid, liquid, or gas, at any combination of temperature and pressure, where the horizontal axis shows temperature, the vertical axis is pressure. The boiling point is the boundary between the liquid and gas phases, which shows as the curved line in this diagram. As the pressure goes up, so does the temperature at boiling, or vice versa, all following that line. And the table at the right shows some of the same boiling point curve values for pressure in psi and temperature in degrees Fahrenheit, in the range that's really of interest here. Storage in propellant tanks is higher, so they will be warmer. I believe the working pressures for Starship are somewhere around 70 to 90 psi, pounds per square inch. Going from atmospheric pressure, which is close to 15 psi, up to 90 psi increases the boiling point by about 40 degrees Fahrenheit, as you can see in this table. This assumes that only oxygen is present, which applies in normal Starship operation. They've worked to eliminate using helium as a pressurant, although it's possible they may need it in the tankers during propellant transfers as a way to push the propellant through the transfer lines. So, what's the problem here? Isn't space really cold? Isn't it only a few degrees above absolute zero? Well, yes, but the problem is really heat transfer. How do you cool something down? You transfer heat. Based on living on Earth, our experience tells us that the bigger the temperature difference between a hot object and its surroundings, the faster it cools off. And that's true for conduction of heat through solids, like carrying heat through a brick wall or a piece of metal. But there's no contact with solids outside the spacecraft, so that's not relevant. Now, temperature difference in liquid or gas matters as well. For instance, for a car radiator, you use the fan to blow air through that radiator and carry the heat away. Using air, that's convection, removing heat by moving fluid, whether it's gas or liquid. And that also is faster with bigger temperature differences. But there's no air molecules in space to carry that heat. So all that's left for heat transfer in space is radiation. The difference in temperature between the spacecraft and space is irrelevant for the cooling. Now, conduction of heat does apply for moving heat around inside the spacecraft, and convection can also occur inside the spacecraft if it's pressurized. But again, transferring heat on or off the spacecraft has to be by radiation. Now, for radiation, the heat removed is proportional to the absolute temperature to the fourth power. Overall spacecraft heating or cooling results from the net effects of incoming radiation from sources like the sun, and cooling by radiating away the heat with that fourth power law. Here's an example. The James Webb Space Telescope. Incoming light is focused by the parabolic dish on a mirror, reflecting light back to the sensor at the center of that array of the golden hexagons there. For maximum sensitivity, they need to cool that sensor down to minus 447 Fahrenheit, getting pretty close to absolute zero. There's a set of solar cells at the bottom of this picture, and then solar shades to block out incoming solar radiation. The sun would be below that craft, as shown in this drawing. So the shades also minimize the conduction of heat from the sunny side to the rest of the craft, and ultimately to the sensor. Those five silvery-looking thin film reflectors, they're very carefully arranged at slight angles to each other, so that excess radiation bounces around between them and finally escapes headed away from the telescope. Now, this spacecraft, it took months to get at its final orbit, near the Earth's sun L1 point. On that trip, it was cooling down all the way, from the warmth it had while it was on Earth. Once they arrived at their orbit, then those shades were deployed. It took weeks after that to cool down even further. But the best those shades could do, all five of them plus the solar cells in the way, the best they could do is getting down to about minus 296 Fahrenheit. Getting down to minus 447 took an electrical cooler. They're closer to the sun, so things are a little warmer there. But this should give an idea of the difficulties in efficient cooling in space. So, boil-off of cryogenic propellant is a challenge in space, whether on a depot or any other spacecraft. Near Earth, the biggest source of incoming heat is radiation coming directly from the sun, but there's also light reflected from Earth, for instance off of clouds and oceans, the albedo effect, and Earth itself is warm, so it sends out infrared light at lower frequencies. Then there's heat from onboard sources like the rocket engines as well. Any of this heat that finds its way to the propellant tanks has to be removed. Without active cooling, this incoming heat is absorbed by increased temperature, then by the latent heat of vaporization of the propellants when it boils off, and then ultimately the heat is carried away when the gas is vented to space. So, what are some of the solutions for boil-off problems? Sun shields can block most radiation, and insulation can slow conduction or convection through the craft. That's passive, requiring no energy to operate, but does add weight. For instance, look at the propellant depot concept pictured in the lower right corner. This was a proposed depot by the United Launch Alliance back in 2011. It is drawn with one shade on the bottom left-hand side covering up a propellant tank inside of it. That blocks radiation from the sun and also light reflected or radiated from Earth, depending on the orientation of the depot. It also directs radiated heat away from the depot. If a solar shade is not enough, you can go to active cooling, refrigeration, which requires power and weight and more parts to fail. Now, another approach is to simply accept some boil-off, but try to use it productively. For instance, for spacecraft with humans, you might think about using the oxygen for breathing. More generally, you could burn the propellants to generate power. A simpler approach, though, is to burn it in small thrusters for controlling position and orientation or settling liquids. Or the even simpler solution is simply using thrusters without burning. That's called cold gas thrusters, as used on Starship. They just shoot out gas driven by pressure. Otherwise, the propellant must be vented to space. Now, this slide shows only one sunshade. The full proposal has two, as shown in the next slide. The red lines indicate the solar shades. With this conical design, they can be very precise about the radiation input from the Sun and Earth based on the orientation of the depot. Note also that this depot is based on joining the upper stages of existing and modified rockets, the Centaur. This is a natural approach, since these vessels already have tested versions of most of the equipment needed: pressure vessels, piping, avionics, thruster control systems, and so on. And they already have adapters to launch with the first stages of various rockets. So far, spacecraft have not gone to zero boil-off. Instead, there's one additional thing that has been done to reduce boil-off, practiced in particular by SpaceX, and for some rockets in the past as well. That's to subcool the liquid propellant when loading at the launch pad. Think of an analogy, a pan with water boiling on a stove. You can turn off the burner and the water cools off. That's subcooling, dropping below the boiling point. Then, after launch, the heat input gradually raises the temperature and pressure in the tank. The subcooling buys time. It takes longer for pressure to increase enough that it must be released before bursting the tank. So this extends the mission time about a week, considered the typical limit for cryogenic propellants. This subcooling is also referred to as densification because the cooler liquid is more dense. That's a benefit by itself because it means you can pack more mass in the fixed tank size. Who does that? Well, SpaceX does that with both the liquid oxygen and the methane propellants for Starship. It also does this for the liquid oxygen on the Falcon 9. The Intuitive Machines Nova-C lunar lander, they use the same strategy. They probably hold the record for the longest mission using methane and oxygen propellants. The other normal approach is simply to carry extra propellants, anticipating boil-off. These simple strategies, like subcooling at launch and carrying extra propellant, they've worked so far. They aren't going to be good enough for getting to the moon and especially for staying there very long. It's even worse for long missions now being considered, such as going to Mars. That's a 7 to 9 month journey each way at a minimum, not even accounting for storage while on Mars. Hence, the renewed interest in refilling tanks in space. There are other things to consider when planning missions involving refilling tanks in space. Most of the propellant used in getting a tanker to orbit is used up in getting the remaining propellant up there. So the payload of one tanker is much smaller than the amounts needed to fill up a comparably sized mission vehicle. So it takes a lot of tanker launches to fulfill the mission requirements for one target ship to complete the rest of the mission. The SpaceX assumption is about 10 tanker starships per target Starship mission. There are arguments about how many tanker launches will really be needed, but take that as a starting point. You need to load up the mission vehicle with propellants faster than they boil off, and you really want all the tanker launches to complete in as short a time window as possible. Since it takes time to land and turn around the tanker ships, you really need multiple launch and landing pads. That's part of why SpaceX is building a second launch pad in Texas and two in Florida. It's also part of why SpaceX emphasizes rapid reuse of their rockets. SpaceX will demonstrate propellant transfer from one tanker Starship to another Starship from the same launch site within a 4-week period. That test could possibly be as early as next year, although that date is in doubt. This is required as part of the Artemis Human Landing System, or HLS, for the moon. Then they have to do a lot better than that with all 10 tanker launches to actually go to the moon. What is the probability of success for a mission with a depot or other in-orbit refills? Say there's a 98% chance of success of one tanker launch, a 0.98 probability. and suppose you need 10 tanker launches. Then, under some assumptions, to get the probability of success for all 10 launches, you just multiply the probabilities of each successful launch. So in this case, you would multiply the 0.98 by itself 10 times. That is 0.98 to the 10th power, which is 0.82. So that 82% chance of success may not sound so great, but this is fixable by having contingency plans for extra launches. David Chevron and his team of NASA engineers had worked out that you can get the probability of success as high as you need with contingency launches being available. They felt that the simple 10th power argument was used to unfairly stop progress on propellant depot ideas. An assumption in the 10th power sort of calculations is that the launches have no effect on each other, that they're independent events. That does ignore the possibility of, say, a tanker explosion destroying a launch pad, which would affect multiple launches. But that can be addressed similarly, since contingency launch plans will almost invariably include other launch pads. A full analysis of failure probability would also have to include other failure modes, such as failure at the depot or target ship. But those don't have the 10th power sort of scale-up problems of worsening success with increased numbers of tanker launches. There are other challenges for propellant depots. A big one is propellant settling in microgravity. That is, gas getting dispersed throughout the liquid at 0 G. On Earth, gas rises above liquid because of density difference in gravity. But in microgravity, there is no top. Gas can disperse throughout the liquid. This leads to several possible problems. One is that you want the escaping boiloff to be vented that is only gas, but you may have liquid too entrained in it, so you wouldn't benefit from having carried away the latent heat of vaporization. Also, for transfers between tanks, the ideal goal is transferring only liquid, not gas. That's again because a liquid is higher density, so you transfer more mass. It's also because when you're done transferring, you want the propellant in the target vehicle to be able to absorb the heat of vaporization. This is actually a common problem in rockets after shutting down engines and coasting. A typical solution is to duplicate the effect of a small amount of gravity through acceleration, and that keeps the liquid and gas phases separate. This can be done by rotation. However, that complicates docking or adds time and propellant to start and stop. A different approach was used in the Starship Flight Test 3, which was part of the SpaceX NASA contract. This is illustrated in the drawing at the bottom right. They ran a test to transfer liquid oxygen from the header tank, which is the top of the rocket, to the main tank under microgravity conditions. They used small thrusters to cause gentle linear acceleration in the forward direction. That's in the milli-G range, meaning thousandths of Earth gravity. That achieved good propellant settling and transfer. While this was all within one Starship, it did allow validating the fluid dynamic models, which were tricky because of the potential for both gas and liquid phases anywhere, and the microgravity condition. That validation is described in the paper cited for this drawing. The other thing they did for that Starship test was transferring by pressure difference without pumps. Besides eliminating complexity, it avoids the problems you get when you get vapor at a pump inlet. That includes cavitation, where vapor bubbles form and collapse violently, damaging the pump, and includes failure to pump at all. That can happen with fuel pumps in cars on Earth, for instance. The term there is vapor lock. For this test, they pressurized the donor tank with helium, presumably for convenience in testing. Normal Starship goals are to eliminate consumables like helium, so they're probably going to use our normal pressure control systems when transferring between the main tanks in real use. Another problem is that propellant sloshing around during maneuvers can complicate docking. Sloshing is a typical problem in rockets, solved with a lot of baffles to break up motions. Finally, there's a general issue of having fully reliable automated docking and transfer systems. Other space-related videos or slide presentations by me are available at the link shown here. That includes a list of videos at my YouTube channel, so you can view them or subscribe for notifications about future videos. These presentations are mostly made as part of the meetings of National Space Society's North Houston chapter, and the link to that is shown. Topics like these are presented as part of a monthly news segment, and there are also lots of other interesting speakers and open discussions. You can attend in person or online via Zoom. Come join us.